Hello, my name is Egon Willighagen. I wanted to talk a bit about a presentation I gave recently at the Dutch seminar at a research group at the Radboud University in Nijmegen. So that's why I kept this slide. Um, because I had a meeting there talking about bioschemas. Because yeah, one problem that we have been having is how do we know where on the internet bioschemas is being used, and they actually were involved in a project that might solve that. So yeah, I have been involved in bioschemas for some time, involved in a molecular entity and chemical substance, and I've been using it for a lot of time. Um, and though I cannot join all the meetings, uh, but otherwise, I'm a researcher at Maastricht University, and you find my Mastodon account there and my ORCID for the people who do not know me. This is the abstract of the presentation I gave, and in bold I have the keywords there. So finding the research, the databases, but also the long tail, and that is really where an internet web-wide indexing comes in, because we kind of know. The databases that have schema.org annotation or bioschemas.org annotation. But what about that long tail? So yeah, I spoke a bit about the history of bioschema.org and Elixir Europe, and at the end the OpenWebSearch, and that is what I'll go into, because I think yeah, meshing the two up. Yeah, maybe I missed something on where we are, but I see a lot of potential there. So the databases and the links to them, I gave an idea of what we have been doing or what we're doing with semantic web approaches in the life sciences and in the linked open data cloud, linking all sorts of databases, and also this, of course, in Elixir Europe. So indicated a number of the databases of Europe, and around that, I focused a bit more on the life sciences there. So there we have these Sparkle endpoints, for example, with a lot of information there. And yeah, and resources that are very relevant for our thing. And also the point here that is, yeah, well, these large databases, and we know how to access them. They have Sparkle, they have other APIs, but we need to, yeah, have other ways, know other databases as well. Some of that, those long tail databases are small databases that we also in our group make available. So we actually have an instance of the Spark endpoint of Campbell. We have Wiki Pathways. We have RDF for AOP Wiki, but we also have a couple of more yeah, more obscure databases that we want to be more findable. They are interoperable, but if no one finds them, so that long tail. Um, and yeah, and this is yeah, the corner that we occupy. But I'm also very much interested in yeah, what are all the databases in that very long tail of databases that I do not regularly run into, that I want to find anyway. So indexing and schema.org. I told them a bit about schema.org because yeah, it was a different community, so a bit of the history of that, what they have. So some metadata about a lot of different topics, like those here, and how that is annotated in web pages, yeah, and that the metadata can be quite limited, and but actually, if you go to all the optional things that you can add, it's quite rich vocabulary of things that you can yeah, annotate metadata with. I moved on to bioschemas. Yeah, well, I mean, you all know this. This is actually, I'm not entirely sure if this is really the first bioschemas article or thing to cite, but that is the oldest that I could find. So I took this one. And indicated that Bioschemas has been working on yeah, on extensions of schema.org for the life sciences. Life sciences related research, also computational tools and courses and what's not. The things that we're discussing in this meeting. Again, yeah, so for the chemistry, because that was the focus that I put in that presentation with relation to the research that we do in Maastricht, the molecular entity with its properties, its fields, and yeah, and that we have been using. So I've been using that, for example, on one of our projects, Scolia, and there we have information about chemicals, in this case a lipid, or a class of lipids actually. And wrapping around things that we have in Wikidata, but visualized in a bit more chemical way. But with the schema.org, in principle, findable, but you need to know which pages have that. And in that long tail, we actually have quite some things from research project in the nanosafety field. We're using the chemical substance profile, for example, to annotate data sets and the materials that they are about. So that ontology IRIs for JRC representative industrial materials, that has ontology identifiers for those JRC materials in that first column there with the codes JRC and M, and we have the bioschemas annotation in that file, so that theoretically indexes can index that. Sorry. This is another example from the nanosafety fields. Here we're annotating data sets, but here too we actually want to know what nanomaterials are these data sets about. So we should not just have annotation of the data set here in these files, but also of the chemical entities studied or described by that data set. Well, it's all nicely findable. So Google indexes schema.org, and for datasets they have a separate search engine. They don't have a search engine for chemistry or any of the other bioschemas originating entities, as far as I know. But we're interested in that. Yeah, this is just another database about identifiers. Yeah, multiple synonyms, but actually only six different materials, and you can link that material also to a lot of different documents. And again, we're using the chemical substance type from bioschemas here to do that. Now, getting into the problem that we have. So how do we link? How do we index that long index of science? So this is one of the biohackathon papers of 2.5 years ago, and we had a project there indexing bioschemas for chemistry and for plants. And so yeah, this described in this preprint and biohack archive, you can link it. But the problem that we there had is, well, we know the large databases, but we actually would like to search the whole internet, and finding the really small web pages, the small databases, maybe just a web page from an individual researcher saying, hey, today I'm interested in this chemical. We want to search it all, because if we can search it all. So what we did in that biohackathon project, we got the information together that was stored in the Sparkle endpoint, and these are some Sparkle queries from that paper. So that you can actually do some reasoning. You can find, okay, hey, I have this chemical here. Find what web pages on the internet also have that chemical, or if you include some chemical logic with the IDSM Sparkle endpoint, for example, what are web pages that describe chemicals that look a lot like the chemical I'm interested in? So the kind of thing that you can do with Sparkle if you have that indexing in place. But at indexing, we did not have that in place. We ended up actually not even scraping from this database, but basically creating data sets of schema.org JSON-LD files for those data sets. And these are two of them listed here. You can see it in the article. So that was a quick introduction of what bioschemas is, and what problem we have. And then the OpenWebSearch, that was the project that the group that I visited in Nijmegen has been involved in. And the OpenWebSearch is creating this index of web pages on the internet. But if we want to index as in that biohackathon project, if we want to index the bioschemas, if we want to index the chemistry or the proteins or all the entities that we have in bioschemas, then we need to know what are the web pages that have that kind of annotation. And since it has been out of reach of bioschemas.org as a project to index the full internet, can they do that for us? So we do not know how to scrape the full web. We don't have the resources for that. And yeah, it is not just the big databases that we already know, like Cabby or Coconut and so it's that have that annotation. But really, that that long set of web pages with small bits of information, like some of the examples I showed. Now, that was basically the end of the presentation I gave, and we then started discussing things. So the next couple of slides is what happened after that. So, well, the website, this is actually the website of OpenWebSearch. It was an EU funded project, and yeah, the goal promoting Europe's independence for web of science. And you can see that, and you have the link here, so you can go there to read more about that. And this is what their index looks like. So they're crawling the internet. They're doing that in a distributed way. So they have a number of partners doing this. I do not know how they distribute the work, and they are indexing things, and they're re-indexing pages as well. So there's a continuous flow of files and of parts of the index. And this open web index, that repository, has a lot of data sets. I don't see the number here, but this is just the first 6 that show up. You can see them collected by collection date. So when I looked at it, actually, it was the 26th or 27th of February. So they're not actually indexing every day, because then we would see an index after the 25th of February as well. But you can see that it is pretty recent. The other thing that you can see here actually is that idea that yeah, they come from different partners. They uploaded here. There are some instructions using a command line tool how to download this data set. But you can also see the differences in sizes. So some this file in the bottom middle is only 305 megabytes, but we also have one here of 130 gigabytes. So an order of 40 times the smallest that we have here. And this is just the first 6 data sets. If you open one of those files, what you will find there is actually a data structure. They have a file of a directory structure where the first directory is the year, and then the month and the day. So you get some metadata there as well, and then a language. So I'm not entirely sure what that language is based on or why they do that, but you get the idea. So for that day, the 25th of February, from this index, we see these Parquet files. So Parquet is a file format for sharing data that I was not particularly familiar with before, but it is for sharing databases basically. But there are multiple files. So even within this single file, there are multiple files here that we have. But now the good thing is that this file actually has a JSON-LD in there. So this index that they have, it already extracted the JSON-LD, the schema.org annotations. So the idea now is where we are, iterate over those thousands of Parquet files, and that is basically the edge where I am right now, because I I do not know how to do that yet. But we have the all those Parquet files. We can just parse them one by one, so it parallelizes quite well, I think. And we can just scan the JSON-LD. Do we find molecular entity in there or chemical substance? The 2 of the bioschemas types of profiles that I would be interested in. And if so, extract the JSON-LD for further indexing. So so on the web interface, the first web interface actually here, or on the index here, one of the two, you can do searches. You can do searches there as well, but I don't think you can search there on the field for JSON-LD as we did in this script here, because then it might possibly be able to search over all those Parquet files in anyway, if they index it. So that is basically how far I got and what I wanted to present here, and see, yeah, how would we want to take this forward? Because I think it would be really interesting. So I'm happy now to actually close the slides and start discussing what the next step would be.